Cyclic voltammetry is an electrochemical technique used to study the redox properties of a solution or a material. It involves applying a potential to an electrochemical cell and measuring the resulting current as the potential is varied over time. The potential is usually swept back and forth in a repetitive cycle, hence the name, cyclic voltammetry. In a typical cyclic voltammetry experiment, the working electrode is placed in a solution containing the electroactive species, and the potential is swept between a positive and a negative value relative to a reference electrode. The current that flows between the working electrode and the reference electrode is measured as a function of the applied potential, resulting in a plot of current voltage curve called the voltammegram. The voltammegram obtained from a cyclic voltammetry experiment provides information about the redox properties of the electroactive species in solution, including the standard potential of the redox couple, the electron transfer kinetics, and the concentration of the electroactive species. Setup of cyclic voltammegram. The experiment is carried out in an electrochemical cell, which is a glass vessel that can hold all of the electrodes in place, without touching each other and causing a short. The cell has a 3-electrode setup. The working electrode is usually made of an inert material. Glassy carbon, platinum, and gold are the most common, with a high polish and a limited surface area where the relevant electrochemical processes will happen. This is because we want the surface of the electrode to be reproducible and to always provide us with the same measurements. Popular choices are calomel and Ag, silver 1 chloride electrodes. Finally, the counter electrode is the electrode to complete the circuit. It is connected to the ground and has a polarity opposite to that of the working electrode. It should have a very high surface area compared with the V, such that reactions are never limited by it. Popular material choices are graphite rods and palladium and platinum wires. Mechanism of cyclic voltammetry. The mechanism of cyclic voltammetry involves 3 main stages. Charging the double layer. Initially, when the electrode is immersed in the electrolyte solution, a double layer is formed at the interface of the electrode and the solution. During the first cycle of voltage sweep, the potential is swept from a low value to a high value. As the potential is increased, the double layer is charged, and the current starts to flow in the opposite direction. Faradic reactions. When the potential reaches a certain value, a Faradic reaction occurs, where the electroactive species in the electrolyte solution reacts with the electrode surface. This reaction results in the transfer of electrons between the electrode and the electroactive species, generating a current flow in the direction opposite to that of the charging of the double layer. Reversal of the voltage. In the next step, the voltage is reversed and swept from the high value to the low value. During this phase, the charged double layer discharges, and the Faradic reaction is reversed. The resulting current is measured, and the process is repeated cyclically. By measuring the current as a function of the applied voltage, the voltammegram can be obtained, which provides valuable information about the redox properties of the electroactive species, including the standard potential of the redox couple, the kinetics of electron transfer, and the concentration of the electroactive species in the solution. Application of cyclic voltammetry. Cyclic voltammetry has a wide range of applications in various fields. Electrochemistry. Cyclic voltammetry is commonly used in electrochemistry to investigate the redox properties of different materials and the kinetics of electrochemical reactions. It is also used to study the corrosion behavior of metals and alloys. Material science. Cyclic voltammetry can be used to characterize and optimize the electrochemical properties of materials such as batteries, supercapacitors, and fuel cells. It is also used to investigate the electrochemical behavior of polymers, coatings, and other surface modifications. Biochemistry. Cyclic voltammetry is used in biochemistry to study the electrochemical properties of enzymes, proteins, and other biomolecules. It is also used to investigate the redox properties of biological systems, including the mechanisms of electron transfer in biological membranes. Environmental science. Cyclic voltammetry is used to study the electrochemical behavior of environmental pollutants such as heavy metals, organic pollutants, and pesticide. It is also used to investigate the electrochemical treatment of wastewater and contaminated soils. Analytical chemistry. Cyclic voltammetry is used in analytical chemistry for the detection and quantification of electroactive species in complex mixtures. It is also used to investigate the electrochemical properties of pharmaceuticals, dyes, and other chemical compounds. Overall, cyclic voltammetry is a versatile and powerful technique that provides valuable insights into the electrochemical properties of various systems, making it an essential tool for research and development in many fields. Application of cyclic voltammetry in cancer studies. Cyclic voltammetry has been applied in cancer studies for the detection and analysis of cancer cells, as well as the development of cancer therapies. Some of the applications of CV in cancer research are: detection of cancer cells. Cyclic voltammetry can detect cancer cells based on their electrochemical properties. Cancer cells have different redox properties compared to normal cells, and CV can distinguish between the two types of cells based on their electrochemical behavior. This can be useful for the early detection of cancer and monitoring the effectiveness of cancer therapies. Study of cancer metabolism. Cyclic voltammetry can investigate the metabolic activity of cancer cells. Cancer cells have a different metabolic profile compared to normal cells, and cyclic voltammetry can measure the consumption and production of different metabolites in cancer cells. This can help to understand the metabolic pathways that are important for cancer cell survival and identify potential targets for cancer therapy. Development of cancer therapy. Cyclic voltammetry can develop and optimize electrochemical therapy for cancer. Electrochemical therapy involves the use of electric fields or currents to target and kill cancer cells. Cyclic voltammetry can investigate the electrochemical behavior of cancer cells and identify the most effective parameters for electrochemical therapy. Screening of anti-cancer drugs. Cyclic voltammetry can screen anti-cancer drugs for their effectiveness and selectivity toward cancer cells. Cyclic voltammetry can measure the redox properties of cancer cells treated with different drugs and determine the most effective drug candidates for cancer treatment. Overall, cyclic voltammetry has the potential to provide valuable insights into the electrochemical properties of cancer cells and the development of cancer therapies, making it a promising tool for cancer research.